I was really pleased when Dick asked me to come down and give a talk about geothermal energy. It's something I love talking about, so the biggest danger is that you'll still be here at midnight and I'll still be droning on about geothermal energy. It's something which I'm doing a fair amount of research in at the moment, and I also teach our students something about geothermal energy. And the image you can see there in the background, that's the Geysers geothermal plant in the US, which is the world's largest geothermal plant. And we'll say a little bit about the geysers and how it works and so forth as part of the talk as we go through over the next hour or so. So I'll aim to talk for about an hour and then take some questions if that's okay. So I was really pleased. I saw on the flyer that Dick sent around that he'd included a figure from one of his publications. And it's great because it's a very clear and simple explanation of the principle of generating electricity from geothermal. So I thought I'd start with this. So in principle, it's very simple. We can produce some hot water from some underground formations where it's stored, pass it through a turbine, generate electricity, and then re-inject the waste cool water back into those underground formations. That's a very simple and concise way of explaining the principle of this geothermal electricity production. What I want to talk about is maybe some of the ways in which it's not quite as straightforward as that in some ways, and also how we can use geothermal energy in other forms, not just for electricity generation. So the overall outline of the talk is just to say a bit about what geothermal energy is, and then say a bit about different types of geothermal energy. So as we just saw there, using it to generate electricity, then thinking about whether, well, we'll see there's some geological controls on where it's really favourable to do that. So can we push this idea out more broadly and generate electricity essentially anywhere? And then I'm going to say a bit about using geothermal energy for heating and cooling, and I'm going to say something about storing energy underground and why that's useful. And I'm going to finish by just touching a little bit about what we're doing in terms of geothermal in the UK. And if I haven't droned on for too long and we have some time, I might just take a little look into the future of where we might be going with this over the next few years. So what is geothermal energy? It's essentially energy stored in the form of heat beneath the Earth's surface. So geo, Earth, and thermal heat. And the Earth has an absolutely enormous resource of heat that we can draw on. So we can look at a profile of temperature through the Earth, right from the surface through to the core, and we can see that we reach some very, very high temperatures as we move into the interior of the Earth. And a lot of that heat is coming from the decay of radioactive isotopes. In fact, it's being generated all the time within the Earth, primarily uranium and thorium and potassium and so forth. And the rest of it is left over from when the Earth first accreted. And the Earth is in fact cooling extremely slowly. The rate of heat loss over the Earth's surface is very small. And so we interpret the temperature in the mantle, sort of the bit right underneath the crust, to only have decreased by about 300, 400 degrees in 3 billion years of Earth history. So we're actually retaining heat very effectively within the Earth, and that's a resource that we can use. But the bit that we can use is really only right at the outer part of the Earth's crust, within a few kilometres beneath our feet. So a huge amount of resource, but it's very difficult for us to access it very deep down. Right, and so the principle of producing geothermal energy is simple. We essentially transfer heat from depth to the surface by fluid flow in boreholes. And what we want to do is to design essentially a subsurface heat exchanger which can take the heat from the rocks or from the fluids and bring it to surface where we can use it. And we really have two main ways of doing that. So the first is what we'll call closed loop, and you'll hear that a few times through the talk. In a closed loop system, we don't actually exchange any fluids with the surrounding rocks. All the fluids stay within the borehole, and they take heat in by conduction from the surrounding rocks. So we can pump water down or fluids down within the borehole and bring them back to surface. In an open loop system, we actually pass fluids through the rocks underground. So we can inject cool water down one borehole, heat it up in the ground, and then bring it back to surface through a hot borehole, and then use it usefully. So in open loop systems, the carrier fluid, so the fluid that we use to transfer heat, is generally groundwater. Okay, it's the water that's naturally present in the rocks underground. And we can pass that water down and bring it back up again. And that means that our geothermal reservoir has to have some key parameters to make this work efficiently. It has to have heat, otherwise it's not a geothermal reservoir. But we have to be able to get the fluids through it, so there have to be fluids present, and the rocks have to be permeable to flow. So in fact, if you're coming from a petroleum geology background, very similar considerations as we would have for an oil reservoir. We have to have flow and we have to have fluids, but we also have to have heat. And ideally, and I'll show some examples of this, we'd also like to have a seal and a trap structure to keep those hot fluids confined within the reservoir and stop them just leaking out into the surrounding rocks. For closed loop systems, we don't have to use water as the carrier fluid. We can use something else. We could engineer that fluid because it should never leak out of the borehole and into the surrounding rocks. So we can design that in a way that means that we don't have corrosion and so forth. And in both of these systems, if we drill more boreholes, we can increase the power that's being delivered from the geothermal system. And you'll see in some cases we drill hundreds of boreholes to make these systems produce enough heat to be economical. So one of the first ways in which geothermal systems are characterized is really in terms of depth that we're operating and the depth of the geothermal system, which is directly related really to its temperature. And so typically if we want to generate electricity, we have to go deeper because that's where the hotter rocks are. I'm going to look at that first. But we can also make use of much shallower resources for heating and cooling. So this would be of order kilometers depth for our deep geothermal for electricity generation, but maybe just a few hundred meters depth for these shallow geothermals for heating and cooling, actually. I'm going to show you how we can use geothermal for cooling as well as heating, which is becoming increasingly important in a heating climate. So the other way we would kind of classify geothermal resources is in terms of temperature, or more technically the enthalpy of the fluids that will be coming out of the ground. And what we see is essentially to generate electricity, you do need to have really rather hot water. So typically for electricity generation, you want it to be over a couple of hundred degrees C, okay? And ideally going right up to these very high temperatures here, where we even may have mainly steam production rather than hot water production. And once we drop below around about 125 degrees C or so, there's not enough heat, there's not enough energy in the water for efficient electricity generation. So now we're really talking about using that for heating of buildings rather than for generation of power. So essentially then, what we can see is that if we have nice hot water, typically from deeper reservoirs, we can use geothermal for electricity generation. We can do that almost anywhere because electricity is very easy to transport over long distances. And essentially the reason why we want that water to be nice and hot is that our turbines are much more efficient when we have much hotter water coming into them. And as the water temperature goes down, the turbine efficiency goes down and we can convert less of that heat usefully into electricity. If it gets too cool, now we're really looking at heating and cooling. We can do that economically, as I'll show you, even with low groundwater temperatures, but we have to generate that heat where we use it. We can't transport heat over long distances, so it has to be really almost right under the building that you want to heat or you want to cool. And we can use heat pumps, which you may have heard about in the news. There's a lot of talk about heat pumps at the moment. We can use heat pumps to change that temperature, to boost it for heating or drop it for cooling as required. So, one of the things that we know about the Earth is that the temperature generally increases with depth. But that increase in temperature varies enormously depending on where you are. So if you're at Larderello, for example, in Italy, which is where we have the world's oldest geothermal plant, the temperature increases really rapidly. This is temperature plotted against depth here. And you can see that at just about a kilometre or so, we're at about 200 degrees C. If we move to other places in the world, the temperature increases much more gently with depth. So this would be the average shown here in red. We can see even places where we have below average increases in temperature. So to get to that same 200 degree temperature, if we look at the average temperature variation, we have to be down at around 6 kilometres. That's a lot deeper than the 1 kilometre we have at Larderello. And those high temperatures are typically associated with recent or active volcanic and magmatic activity. That immediately, if we want to see very hot systems for electricity generation, then tells us where we need to be looking in the world to find those kinds of hot systems. So we're looking basically for systems like this where we have evidence of lots of heat and fluids at the surface, which we can relatively easily tap then for electricity generation. And this is a photograph of a natural geyser field in Iceland. But we could take very similar pictures in New Zealand and lots of other places around the world. So now we have a very basic control coming from tectonics, essentially, on where we have the right places for electricity generation. So what we're looking at here is a map of the main tectonic plates. We can see that the mid-ocean ridges passing through here, they really stand out on this plot. We've got subduction zones shown in green here, and we've got some rifts, so some intracontinental rifts shown here in yellow, where we're trying to open up the crust and maybe even form a new ocean. And the red spots are where we have active geothermal plants. And you can see they're very strongly linked with these major tectonic plates, because that's where we see lots of magmatism and volcanism, and also associated with places where we have hotspots like Iceland and so forth. So we see a really direct link between active geothermal electricity production and where we have active volcanic or recent magmatic systems, because that brings heat very close to the surface for us. So one of the reservoirs we can look at here is Larderello in Italy. That's part of a sort of a rifting region, an intercontinental rift. And in fact, that's associated with some very recent intrusions of granite, which is still very hot. And the great thing about Larderello is it brings all the elements together that we need for an active geothermal system. We have a source of heat from these recent intrusions. We have a fantastic permeable porous aquifer, which is in fact a fractured limestone, so it's a sedimentary rock. We have a nice cap rock that's impermeable, that sits above that, which is impermeable shales and clays, so all the fluid is retained within the reservoir. And we have a trap structure, which is trapping that hot water and even a steam cap within the reservoir, so we can drill wells in there and bring the heat to surface. And in a system like this, it's genuinely renewable, because we're bringing water into the reservoir from the surrounding aquifer, and that's being heated up all the time, and so we're generating new heat as we take it out. So as long as it's managed carefully, this system will be able to operate for many years, because we are not taking out heat faster than it's being brought into the reservoir. And so Larderello now has been operating for over 100 years. We can look at something similar. This is now moving down to New Zealand, the Wairaki geothermal field. This is all essentially very recent volcanic deposits, but again we have an aquifer, a nice aquifer here, which in this case is permeable volcanic ashes. We have a nice seal rock above that, which are impermeable igneous rocks and lavas, so different rock types here forming the reservoir and forming the seal, but the same principle. We have some little trap structures which are often bounded by faults, and we can form these steam caps. We have very high temperature water, so we get these fantastic geothermal resources that we can tap in these specific locations. And something similar at Long Valley Caldera. And I should point out that all of these systems are essentially operated with these open loop wells. Okay, we pump the groundwater out of the ground, run it through the turbines, then we re-inject it back into the ground to maintain the reservoir pressure. So the one other place that we can look sometimes for these geothermal electricity sources is in very deep sedimentary basins. So here we have sedimentary rocks where the basin has opened up and it's dropped them to be deep enough that we actually have hot enough temperatures even without active magmatic systems being present. And so this is an example from Munich. This is a carbonate reservoir called the Malm aquifer, and it drops down here. This is essentially a basin in front of a big mountain range, in front of the and this is dropping that sedimentary aquifer nice and deep, so we start to reach towards temperatures which are hot enough just about for electricity generation, but are also used a lot for district heating. And this is mainly happening in Munich. So those are the main ideas, places that we have where we can generate sort of the high enough temperatures for electricity generation, and these sorts of plants can be really quite large in scale. So the geysers, which is the picture I opened up with at the beginning, that has about 350 wells, and it generates about 900 megawatts of electricity. And for comparison, that's not far off the scale of a major power station. I put Heysham 2 there because I grew up near Heysham 2 power station, nuclear power station. That's around about 1,200 megawatts. So these large geothermal reservoirs or geothermal plants can approach that kind of scale of a large power station. But because of this relationship between active magmatism, tectonic plate boundaries and so forth, there aren't that many locations in the world that host these hydrothermal systems that can be used for large-scale electricity power generation. So top is the US, and essentially all of these other countries here are really well established to have close links with active magmatism and active volcanism. And if we actually look at how much geothermal electricity we're generating, it's only around about 0.5% of the worldwide demand. So at the moment, geothermal electricity is a pretty small component of worldwide electricity generation. So, can we do something about that? We know that temperature increases with depth. So, why don't we just drill deeper and get to those depths where the rocks are going to be hot enough that we can still generate electricity? There are a few problems with that. So, as Rob would know, that's going to cost you a lot of money, okay? To drill a well, potentially to 7 kilometers, potentially through hard igneous rocks, is not going to be a cheap well to drill. The other big problem we have is that we wanted that porosity and that permeability to host the fluids and allow the fluids to flow through the rock. And generally, the deeper we go, the lower the porosity and permeability are going to be. And once we move out of sedimentary basins, we're typically in crystalline basement, igneous rocks, metamorphic rocks that have naturally low porosity and permeability. And that means that if we want to exploit these deep reservoirs, we typically need to create permeability and introduce fluids into the system because they're not naturally there. And we call these reservoirs hot, dry rocks. And so there's a huge amount of interest in the moment in trying to essentially generate hot, dry or develop hot, dry rock reservoirs. To extend, the use of high temperature geothermal beyond those natural hydrothermal systems associated with active magmatism. So exploit heat in rocks that are hot, but they're dry and they're non-porous and they're impermeable. To do that, we need to create flow paths in the reservoir rock. We need to create fractures, and we need to be able to inject water from the surface and then cycle it through the rock. So the reservoir has heat. Can we add fluid and permeability? And the answer is yes, we can, and it's been demonstrated in several places around the world. But it comes with some risks, okay? Because you have a risk of induced seismicity associated with opening those fractures. So in the UK, most of the concern we've had around fracking was to do with shale gas and so forth. But in other places around the world, they've been much more concerned about fracking related to the exploitation of hot, dry rocks. So there were issues in Basel you may have seen in the news. In fact, there was the developer was threatened with court action and prison for an earthquake that was linked with the development of a hot dry rock project there. There was a major earthquake in Pohang, Korea in 2017 that caused a lot of damage and injuries, and that was associated with the development of a hot dry rock project. And one of the great risks then, of course, is that a technology which is very low carbon, provides steady baseline supply, it's a fantastic replacement for fossil fuels, begins to have a very negative perception with the public because they associate it with risks rather than benefits. And so in fact there's a kind of a part of the geothermal community which is a bit dismayed by this, because if we're going to have earthquakes happening around the earth, around the world, which are linked with geothermal, that can create a lot of negative perceptions about a technology that doesn't have to use fracking and in many places will be perfectly safe to operate. So this is really where we are with high temperature geothermal for electricity generation. It offers baseline low carbon electrical energy, but at the moment to use those natural hydrothermal systems we're really rather geographically limited to active magmatic locations, typically associated with plate boundaries. And it's been very difficult to try and extend the principle more generally to hot dry rocks because of this issue around having to create fractures to allow fluids to pass through them. So one of the things that's being looked at is whether we can use something called like a radiator well. So the problem with using wells on their own, as we'll see in a bit later on in the presentation, is that they're very poor heat exchangers because they have a very small surface area to exchange heat with the surrounding rocks. If you have a single vertical borehole, it has a very small surface area for that heat exchange. can we drill really smart wells where there are many, many laterals coming off a motherboard which are actually connected to form a closed loop, which could massively increase the area of heat exchange, like a radiator in your house, but without having to create fluid flow paths in the reservoir with the associated risk of seismicity. So I think there's lots of promise in deep geothermal for electricity generation, but I think you have to be doing it in the right place. So I guess what I want to move on to in the second part of the presentation is the other way we can use geothermal, which is for heating and cooling. And the reason I like this a lot is because its potential is very geographically widespread. It's much less limited than deep geothermal for electricity generation. So we're going to move now into this shallower domain, looking at the upper few hundreds of meters typically of the Earth's crust. And I think it's rather the unsung. Most people, when they think of geothermal, they think of electricity generation, they think of the geysers, they think of steam. But I think this has, in some ways, more potential to make a big contribution to low carbon energy generation around the world. So if we talk about kind of medium geothermal, this would be temperatures high enough to use directly for heating. And this takes us back into sort of deep sedimentary basins and so forth. So this is a map of Germany, Munich down here, and this is the reservoir that we talked about before. And often medium geothermal for heating is kind of right at that cusp between, is it hot enough for electricity generation, or is it only going to be hot enough for heating of buildings? And the real thing we struggle with here is maintaining those porous and permeable aquifers. It has some shared problems with hot, dry rocks. We want to have naturally porous and permeable aquifers. You know, this Malm aquifer is a little bit unusual because it was preserved to these relatively significant depths, about 5 kilometers here. I realise for those of you at the back, this must just be occasionally a bit of a vague image you're getting. I didn't realise I should have made these much bigger, but I do apologise for that. And there are plenty of places where we've tried drilling wells to these kinds of depths to produce geothermal energy for heating, and we found the rocks are dry and we found the rocks are impermeable. So there was an example of that in the UK. There was a well drilled on Newcastle. It was intended to be an open loop well that would heat a whole series of buildings at the surface, but then when they tested it, it was dry and it didn't flow at all. So we've had some failures where we tried to target some of these deeper sedimentary rocks to bring heat to surface from them. What we can do instead is to stay shallow and use a heat pump. So if we look in the very shallowest part of the crust, so now we're only going down to, this is sort of 400 meters here, in the upper sort of 100 meters or so, in fact the temperature stays around about constant. It doesn't really fluctuate very much. If you go right into the upper part, it will get warmer in summer and cooler in winter. But then once you get below about 10 to 20 meters, that heat exchange doesn't penetrate so deep. And so the water and the rocks here are typically always around about sort of 13 or 14 or 15 degrees or so. So whenever I drill, you know, whenever we work with a borehole in London, for example, in the chalk, it's always about 13 degrees. Now, that doesn't sound very much, but it's warmer than cold outside air in winter. So if you can bring that water to surface, it has energy that you can use usefully for heating if you boost it with a heat pump. It's also cooler than the outside air in the summer. So if you bring it to surface, you can use it for cooling. And that's really the basic principle of shallow geothermal. But we would boost those temperature changes using a heat pump. Now, again, when we apply this technology, there are several different ways we can do it. The one that most people are familiar with is what's called a ground collector, where your back garden is dug up and a whole load of pipe work is put in there and it's connected to a heat pump in your individual building. I'm not going to talk about those today, and actually I personally think that this is probably not the right route for us to be going down if we're going to deploy shallow geothermal in a very widespread way. I want to talk about systems that are much bigger capacity than that. So these would supply major buildings like hospitals or schools or universities, and if you want to use them for domestic use, you would do it via a local heat network. And in fact, there are even now companies looking into doing this where you would drill some boreholes on your street and they would basically come and sell you heat as a service rather than the fuel to generate your own heat. So they would then pipe to you from the boreholes groundwater or some other working fluid that would provide you with this feedstock that you could then boost with your own heat pump. And again, we can do this either with a closed loop borehole, where the fluids remain within the borehole itself, there's no exchange, or we can do it open loop, where we actually produce groundwater. So, as a quick aside, because I'm often asked this, what is a heat pump and how does it work anyway? Okay, so I know this is a geological association, but we're going to have 2 slides diversion on just what a heat pump is. I think the name of heat pump is really misleading. It doesn't pump at all. And we all have a heat pump in our house because we all have a fridge. And essentially it uses the same technology as a fridge. So what we do is we have our source of groundwater, for example, that's coming out. And if we're going to use this for heating, we have a fluid with a very low boiling point. And so just adding that bit of heat from the groundwater is enough to cause it to boil. And then we pass it through a compressor, not a pump, we compress it. And that's where the electricity supply comes in. It's to compress the gas, and as you compress it, its temperature goes up. And so then you pass that high temperature via another heat exchanger into the fluid that's then going to heat the building that you're in. That cools the gas, which then recondenses, and it passes back through the heat pump where it's boiled again, and so on and so forth. And so it should really be called a compressor or something like that, rather than a pump. And the thing with heat pumps, and I think this is something that most people are aware of, is the less you have to change the temperature, the more efficient your heat pump will be. So heat pumps are measured, how well they perform is measured by something called the coefficient of performance. And that's the ratio of how much heating energy comes out to how much electrical energy goes in. So a good heat pump will put 4 units of heating energy out for every unit of electrical energy that you get in, which is why it's so much better than using a direct electrical heater. Your kind of fan heater, one unit of heat energy for 1 unit of electricity. A heat pump should be 4 times better than that if it's well, and even higher if you can keep the temperature boost down. So what that means from a sort of geothermal side, okay, I'm not a heat pump person, is I know that I need to produce groundwater at the highest possible temperature for heating and at the lowest possible temperature for cooling, so I can make the heat pump as efficient as possible. That's my job as the geothermal person, and it's the building service engineer's job to make the heat pump work properly and all the rest of it. So that's kind of a constraint on me. Get that groundwater out as warm as possible, as cool as possible. So practically how these would work is that they would be really co-located with the buildings of interest. As we say, we can't transport heat a long way, so you would have some boreholes in an open loop system which would penetrate an aquifer beneath the building of interest. And then we would again produce groundwater from a well, pass it through the heat pump to provide heating, and then re-inject the waste back into the aquifer. And if we can get the wells deep enough, maybe we don't need to use a heat pump, as we've seen for some of those medium depth systems. Now, one of the things we can do, and I'm not going to go through, see, I'm a physicist, right? So there had to be 1 equation or 2 equations in the presentation, but I'm not going to make you go through it. All I'm going to say is this, right? We can make an estimate for sort of how far away that well can draw heat in. And if it's a flowing well, if it's open loop, we have groundwater flow moving in. And if we have to provide heating for about 6 months of the year, and I know how long the well is, and I know how much groundwater I'm going to produce, I can work out about how far away from that well we're going to be able to bring heat in. And typically it's around about 50 meters or 100 meters, something like that. So what that means is that I get lots of power capacity from the borehole, and really this will make more sense when we compare it with a closed loop system. But essentially open loop is great because you get lots of heat and lots of cool coming out of the borehole because you're able to transfer that with the flow of groundwater. The problem, of course, it's interesting if you're a geo person, is that you have to be able to predict flow through the aquifer with reasonably low uncertainty, to be confident that your groundwater flow is going to be fast enough and steady enough to be able to supply the heat or the cool that you need. So that's the bit that is great for geos, but it really puts building service engineers off. They get very worried about the idea the aquifer might not behave as predicted. And we can basically use this to provide heating or cooling or both, okay? So if we want to do heating, we basically produce water at the ambient aquifer temperature, pass it through normally through a heat exchanger. We don't pass the groundwater itself through our heat pump. We take the heat out of it, and then we re-inject the cold wastewater back into the aquifer. And in summer, we can switch it around. We've produced groundwater at the ambient aquifer temperature. Now we take the cool out of it, and we re-inject the warm waste groundwater back into the ground. I'm going to show you a way of doing this that's better in a few slides' time, but this is the basic operation of an open loop geothermal system. If we don't have a good aquifer, okay, so all of this is assuming that we have a nice permeable porous aquifer available. That's not always the case. So in London, for example, if you're happy to go below about 80 metres, you get into the chalk, fantastic aquifer. But if you're not willing to drill deep enough, you've got a huge interval. We've got this 80 metres of London clay, which is impermeable, but you can still exploit that using closed loop boreholes. So if we don't have a good aquifer, we can use a closed loop heat exchanger, which basically works on the same principle. But now we have to rely on conduction to move heat in and out of the borehole. So we would typically have a U-loop, for example, where we inject down one limb and it comes back up the other. Or we might have a coaxial arrangement where you inject down the middle and it comes up the outside. And again, we can do a little back of the envelope calculation to say, well, how far away from the well can we actually get heat or cool into the well? And we can basically do that by assuming it's conductive and again assuming heating for about 6 months. And it turns out that we only get about 8 metres away from the well. So remember, for our open loop borehole, it was 50 metres. It's dropped right down to 8 metres if we have a closed loop well. So what that means is that we have a much smaller power capacity for each closed loop well, which basically means we need lots of wells to do closed loop. So open loop, we can use a small number of wells. Closed loop, we need to have lots and lots of wells to get sufficient heat or cool out of the ground. And this is, I'm going to skip this. It just tells you you have to drill a lot of wells to get heat out. So in practical terms, what that means is if you have a large deployment, you will often find hundreds of wells that have been drilled. Under a car park, for example, there's an IKEA store in Sweden. If you drive into the car park, there's lots and lots of manhole covers, and under each manhole cover is a borehole, it's a closed loop borehole which is sourcing heat and bringing it into the building. And they will design the array in such a way that you kind of maximize the efficiency with which you can get that heat or cool out of the ground. Okay, so that's the basic principle. For shallow geothermal, we bring this relatively low temperature fluids out of the ground, groundwater out of the ground if it's open loop. And we then take its heat or cool out using a heat pump, and then we pass the waste back into the aquifer. So the best we do is that we produce water at the ambient aquifer temperature. But what would be neater? Okay, so I said that in the summer, we're going to be injecting back into the aquifer waste heat. And in the winter, we're going to be injecting back into the aquifer waste cool. What if we reuse that? So instead of just leaving it in the aquifer, what if I store heat in the summer and produce that back out of the aquifer in the winter, and then store that waste cool in the aquifer, and then bring it back out in the summer? And that's exactly what we do in underground thermal energy storage. So this is the energy storage bit, right? What I've talked about so far is geothermal. This is the energy storage bit. And what I like about this is it's more efficient than just leaving the heat or cool in the aquifer after we've used it, because we can bring it back out and reuse it. And remember, my job as the geothermal person is to bring water to the heat pump, which is as hot as possible for heating and as cool as possible for cooling. Now, if I just use the natural ambient aquifer temperature, I can't really change that. It's 13 degrees or 14 degrees. But if I reuse the waste heat and waste cool, then I can start to engineer it to give higher and lower temperatures for heating and cooling. So the two technologies that use this, one's called BTES, borehole thermal energy storage, and the other one is ATES, aquifer thermal energy storage. And that's the one I really like, okay, because it's big capacity and it's very efficient. So what we do in aquifer thermal energy storage, as I said, is that in winter, okay, we're producing groundwater, we're passing it through our heat exchanger, and we're using a heat pump to boost the temperature, and then we re-inject the waste cool water back into the aquifer. In the summer, we switch the wells around. So now, where we had been injecting, we now produce. And we produce cooled groundwater And often it's so cool that I don't need a heat pump anymore. I can just cool the building directly with that cooled groundwater, and then I re-inject the waste heat back into the ground. So when you come into this from, as I did originally, I was a petroleum person, right? And we had injection wells and production wells. It was dead straightforward. And then when I went into geothermal, it was the same. We had abstraction wells and injection wells. Then I moved into this, and it got really confusing because now the wells switch flow direction. And in fact, what we have is a cool well and a warm well. And the warm well is injecting in summer and producing in winter. And the cool well does the opposite. It produces in summer and injects in the winter. So we're switching the flow direction. These are bi-directional wells. We switch the flow direction. And this is great, right? Because now I can bring water out to my heat pump, which is hotter than the ambient groundwater temperature. So my heat pump's more efficient. And in the summer, I can cool, and I don't even need to use a heat pump. So this is way more efficient than conventional geothermal. And if this little movie is going to play, it's not great resolution, but this is a little numerical simulation showing an ATES system in action. This is the aquifer, and that's the building. And the warm plume builds out in the summer and then gets sucked in again in the winter. And the cool plume builds out in the winter, and gets sucked in again in the summer. So we're making these plumes of hot and cool water that grow and shrink as the seasons pass. And there are operating systems around the world, okay? So kind of typical deployments of ATES would be aquifer depths around tens to hundreds of meters. You have to have at least 2 wells, a warm one and a cool one. But these are often scaled up to have lots of wells, so lots of warm wells and lots of cool wells, so they can supply really big heating and cooling capacities. Flow rates of orders cubic meters an hour to thousands of cubic meters an hour, and they can power really big systems going up to tens of megawatts of heating and cooling. So a classical example is Arlanda Airport in Stockholm, which is heated and cooled by one of these ATES systems, one of these big scale ATES systems. Who's really doing this? This is a map showing different countries. You can maybe just about make it out. It's the Dutch. The Dutch have got about 3,000 ATES systems operating at the moment. They are definitely the world leaders in deploying this technology. They have some fantastic aquifers, all sort of basically fairly recent river deposits because they have a pretty big river that passes through there. And the rest of the world is really catching up. There's a few deployments coming in now in Sweden and Norway and in Denmark, but we do actually have some operational deployments in the UK, and they're great because they act as demonstrators for this technology to build some confidence to apply it more widely within the UK. And if we look around the world, so I said that for electricity generation, geothermal contributes about 0.5%. But for heating and cooling, it's about 3.5%. So still a small number, but considerably bigger than electricity generation. So this is kind of why I think that heating and cooling from geothermal is like the unpopular younger brother of electricity generation. Actually, it's really good, and it's a bigger contributor to world energy generation, but very few people have really heard about it, and we don't really think about it as much as we should. And I think that this is really where we can make we can have a very large growth potential because we can do this shallow geothermal stuff almost anywhere. Okay, there's no need to be near volcanic systems or magmatic systems. You don't even need an aquifer. You can do it with boreholes in a tight rock near the surface. So for me, I'm kind of excited about geothermal for heating and cooling. It offers baseline, low carbon heating and cooling to buildings. It's very widely deployable. We don't have to frack, so we don't have these risks of seismicity. We can use naturally porous and permeable aquifers. And if we do it with energy storage, we can get very high coefficients of performance. We get cooling almost free and heating much more efficiently than traditional open loop geothermal. But the real thing here is that we need to be able to accurately predict how the groundwater will flow in the aquifers. That's why I like it so much, because that's what I like doing. I like understanding flow in the subsurface. So the last part of the talk is just to have a little look at what we're doing in the UK. So when we're sort of doing geothermal exploration, one of the things you often look at is heat flow at the surface. Okay, so hot colours here show high heat flow at the surface, and cool colours show low heat flow. And we also do have a fair number of boreholes in the UK, typically oil and gas wells, which have penetrated to about 1 kilometre or more depth, where we can also try and map out sort of the temperatures in the subsurface. You can see lots of bullseyes on this map, and that's really because we have sparse data and there tends to be some bullseyes around some of the wells. So I guess the point is that when we look at high heat flow, what really stands out are these granites down here in Cornwall. And of course, that's where we are currently most actively looking at electricity generation in the UK with the United Downs project and also the, the Eden project. We do have some potential for hotter geothermal elsewhere. So we get some relatively deep basins where we get some reasonably high temperatures. That was the motivation for drilling the well in Newcastle. Sort of some potentially warm, hot, deep sediments, but they were tight. But there is a well that operates in Southampton from the Sherwood sandstone, which is at about a depth of about a couple of kilometres there. And that produces hot water about 70 degrees and provides some district heating to Southampton. But we don't have, we don't have many, that's the only example we have of an operating open loop well in the UK. So in terms of the Eden project, that's where we're looking to try and generate electricity in the UK. It's an open loop project that they are trying to essentially pass fluids through a naturally fractured part of the granite there. There's a major fault that passes through, which is associated with lots of damage to the surrounding rocks. So they're trying to use the natural fractures in the rock to provide a connection between an injection well and a production well that brings water to surface at not far off 200 degrees if this is going to operate well. However, even here, where they've tried to work with natural fractures, there have been some issues around seismicity. So they've been able to manage it very actively. They really engaged with the local population, explained what was happening and why this was happening and it wouldn't be dangerous. But there has been some felt seismicity associated with the Eden project, and I feel this is just always the risk we have with these hot, dry rock projects. In terms of medium geothermal, we have the Southampton well, which is producing a couple of megawatts of geothermal power from the Sherwood sandstone at a couple of kilometres depth. But I think, again, in the UK, the real growth area we have is for shallow geothermal for heating and cooling. So one of the great things about the UK is that we have lots of really good quality aquifers that we've been exploiting for a long time for groundwater usage. So the Chalk aquifer in the southeast, the Sherwood sandstone in parts of the Midlands and the north, and so on and so forth. There are carboniferous sandstones in Scotland. And we know lots about these aquifers because we've been producing groundwater from them for hundreds of years. So we have a really quite extensive borehole database with the BGS, so you can look at characterising the aquifer properties and how how groundwater will flow through them. So we have a lot of good aquifers shown here in green, and even though we don't have good aquifers, we can still use closed loop boreholes for geothermal. And often those aquifers are co-located with areas of high heating and cooling demand in the UK. And I must emphasise, I think cooling is going to become more and more important as we move through the next decades. It can be very dangerous. We have deaths in summer when we have very high temperatures. People can't control the temperature in their own home. So I think we should be looking to offer cooling as well as heating if we can through these low carbon geothermal technologies. And in fact, London is the city in the world with the highest rate of increase in demand of cooling at the moment. It's really going up very quickly. So in fact, in London, we have already around 70 large-scale geothermal systems operating, primarily using the Chalk aquifer for open-loop systems and a small number of closed-loop systems. I'm sorry, that map is just useless, isn't it? I mean, you can't make anything out on there. But the green blobs are active open-loop systems, and they're mostly concentrated around about central London, which is sort of obscured here in the middle of the map. So it's not like we're not doing shallow geothermal in the UK, but there's a lot of potential to grow it a lot more than we have at the moment. So about 70 systems operating in London, and then a handful really operating outside of London, very specific buildings, and there's one or two in Manchester and so on. But again, a lot of potential for growth. So this is something we've been looking at, and in fact we've been engaging with DESNZ to look at solutions for low carbon heating and cooling. It's also, heating and cooling is one of the most difficult sectors to decarbonise, okay, because we're looking at trying to replace millions of gas boilers and so forth in individual properties. So in fact, it's much harder to decarbonise than electricity. Electricity, great, we've got wind, we've got solar and so on, but heating and cooling is really tough. So we've been looking at how much electricity you need for heating and cooling. This is air source heat pumps, so kind of being pushed very heavily at the moment because they're very easy to install. This is traditional groundwater heating and cooling, so there's open loop. This is our UTES system where we store and reuse heat and cool. And basically what you can see is we need to use less electricity for UTES than for any of the others. And that's because we don't need to make the heat pump work as hard. And in fact, for cooling, we don't need a heat pump at all. So that's good for two reasons. One is that it actually puts less demand on the grid. So one of the big problems we have of rolling out heat pump technologies, along with electric cars and all the rest of it, is that National Grid ESO are really struggling now with the extra demand they're going to have to supply in terms of electricity. So it means upgrading lots and lots of grid connections and so forth as everyone starts to put these technologies in their home. The other big thing, of course, is it comes with lower carbon emissions. So the less electricity used, the lower the carbon emissions are going to be. And I'm not going to talk through this graph in detail. The main take-home message is that, you know, this storage technology, aquifer thermal energy storage, it delivers heating and cooling with lower electricity demand and also lower CO2 emissions than conventional open-loop geothermal. It's efficient for heating because we deliver warmer water to the heat pump. I've done my job. And it's very efficient for cooling because we can just directly cool the buildings without using the heat pump at all. So we've actually been looking at, okay, so, you know, is this a big deal, right? So, you know, we've said that internationally, geothermal supplies 3.5% of heating and cooling demand. If it's going to be the same in the UK, then clearly DESNZ should be looking at something else as a solution for the UK's heating and cooling demand. So we've done some kind of probabilistic modelling using Monte Carlo methods, which again will be familiar to many of you who come from the oil and gas industry. So we don't really know a lot of the numbers exactly, but we can look at a range of them and then make lots of forward predictions and come out with some probability distributions. So the first thing we can do, and again I won't go through this in detail, is we can look at how much energy we think these systems can supply per unit area. And then we can look at what the demand is across the UK, and then we can match those two things together to look at how much of UK demand could be supplied. And it turns out that we could meet about 60% of the UK's heating demand and about 80% of the UK's cooling demand if we had a really widespread rollout of these particularly aquifer thermal energy storage technology. So it could be a massive deal in the UK. This is not 3.5%, it's a very big percentage of what we need. And we do actually have some operating systems, so we can demonstrate that it works in the UK context. We have 11 systems altogether, so not many. 10 of them in the chalk and 1 in the Permo-Triassic Sherwood Sandstone in Manchester. And the kind of scales that we have for this is the 11 systems. They typically use 2 to 8 boreholes, but they offer sort of megawatts of heating. So the biggest ones here in London, Riverside Quarter and St James Riverlight, these are 2 megawatt heating and cooling systems. This is not individual houses, and in fact this is a picture of one of the developments that's supplied by an UTES system in Wandsworth in London. This is a big development, there's 500 flats and shops and so forth, and this is being supplied by an 8-well UTES system with significant CO2 savings over conventional CHP plants and so forth. So we have got demonstrators that we can take to the government and say it works, we can show you that, and we can roll it out much more broadly. There's some things we need to think about though, okay? And one of them is that the chalk is a very complex aquifer. So what we see, if we sort of look at the stratigraphy, we've got the London clay in London, and then we've got often the chalk, and often we get some sands that sit just above the chalk, the Thanet sands and the Woolwich beds and so forth. And at the top of the chalk, in lots and lots of boreholes in London, we see huge amounts of flow right at the top of the chalk, just below whatever sits above it, the Thanet sands or the London clay or whatever. So we run flow logs through these wells, we see massive amounts of flow coming into the chalk. And we think this is essentially a karst, okay? So the chalk has been exposed, it's been eroded, and we can go and look at outcrops. So this is a quarry down near Sutton, I think it is. And we went down and had a look at it to show our students kind of what the chalk looks like. And in fact, if you look at the top of the cliff, you can see lots of kind of vertical features in here And this is a karst horizon, and in terms of flow, it's like having a cave system, and so you get huge amounts of groundwater moving through the karst. When we come to look at storage and how an ATIS system will operate in London, this is really important because it affects a lot where the plumes are going to go. So in a nice Dutch system, the plumes form cylinders around the wells. But because we have all of this massive flow unit, this karst at the top of the chalk, this might be where the laptop doesn't manage to do the, yeah, this should be a video, and I don't think it's going to play. No, it's not going to. Oh, that's a shame. Well, anyway, what you would have seen is instead of nice cylindrical plumes, they're like pancakes. They come right out and they spread right along that karst horizon at the top, which means they can interfere with each other, which you don't want. If you bring warm water and cold water together, they mix and you destroy the value of storing the heat and the cool. So one of the things we're looking at is how we might engineer these systems differently in the chalk to avoid that problem. So maybe make the plumes offset vertically rather than horizontally, for example. And we also need to look at things like mixing groundwater of different compositions. So in lots of boreholes in the UK, this is not from the chalk now, this is from the Sherwood sandstone, you often see the water becomes quite saline as you go deeper. So this is plotting chloride concentrations, nice and fresh, it's been refreshed by meteoric water, and then you can move into something which is much more kind of connate, and it's much more saline. But alas, you're not going to see that, I don't think, because I don't think this movie is going to play either. But if it had played, you've seen the salt water being sucked up into the well and then puffed out, because remember, these are bi-directional wells. So what you bring into one well gets injected into the other. So it sucks up the salt and then puffs it out, and then sucks up the salt and puffs it out. And you can start to mix up salt water and fresh water. And we don't want to do that because we don't want to contaminate nearby freshwater groundwater supplies. So there's lots of potential, but we have to be aware of what's happening in the subsurface and how we engineer that responsibly to make these systems sustainable and economic and environmentally friendly. Oh, it works. There we go. I didn't expect that. There we are. You see the salt. So this is the potable water drinking limit for salt. This is very salty water down here. And you can see it's being moved up, and we're starting to redistribute salt into the aquifer, which is not great. So we want to engineer these systems so they don't do that. So I think generally overall, prospects for geothermal, in terms of electricity generation, fantastic where you've got the hot rocks and the fluids. So fantastic where you have these hydrothermal systems associated with volcanism. We're still struggling to extend it beyond that into deep rocks which are hot but dry. In terms of shallow geothermal, it offers baseline low carbon heating and cooling. I think it has real potential for very widespread uptake around the world and in the UK specifically, but we need to be responsible about how we understand the response of the subsurface. So that's why I'm still very busy, okay, because I don't think about fluid flow now for oil and gas reservoirs. I think about fluid flow and heat transfer for geothermal systems. So the last 2 minutes of the presentation before we finish, I'll look to the future. So what kind of things are we kind of working on at Imperial? So I said that, you know, kind of very high temperature systems naturally formed were only located in certain places, and it was very hard to engineer them where the rocks were hot but dry. How about we make them ourselves when we have lots of cheap or free electricity? So at the moment, we have a massive problem with wind curtailment. It's only going to get worse. So as we increase the capacity of wind generation, we get closer and closer to always matching demand, but there are periods now where we generate far too much electricity from wind. So we have to curtail that, and we waste that potential energy. And the electricity price will actually become negative. And so that even now in domestic tariffs, we're getting offers to say we can use this electricity for free. How about, instead of curtailing it, we store it and we reuse it when we need it? And one of the ways we could do that will be by creating our own high temperature geothermal resource. So we take the electricity, we run it through a boiler and heat up water to very high temperature and store it underground. And rocks are very poor conductors, that's why geothermal works so well, so it won't cool down very quickly. And then when we need it, we produce it, run it through a conventional turbine, and then re-inject the waste underground. So we store very high temperature water, and we do it in naturally porous and permeable reservoirs, so no fracking issues or anything like that. That's sort of what we're looking at the moment, and it's attractive because it's absolutely massive capacity compared to any of the kind of human-engineered technologies. So We reckon that we can store sort of order petawatt hours of electricity in the UK if we exploited UK oil and gas reservoirs and deep aquifers, which is just huge compared to even the biggest battery farms, which are also quite difficult to operate. So there's a fire here at the big battery project in Victoria. And it also offers massive, huge power. Okay, so something like Dinorwig, which you might be aware of, that can discharge 1.7 gigawatts, which is big, but it can do it for around about 7 minutes, right? I mean, once you run that thing at high capacity, it exhausts itself very quickly. So good when everyone turns a kettle on at half-time in the England football match, but not very good if you want to have really long-term, large-scale electricity storage. So we think we can store really vast amounts of energy for electricity generation if we exploit the UK's old oil and gas reservoirs, which are now coming to the end of their life. It can delay decommissioning and so save lots of money. And we also have a big and skilled workforce who really know how these reservoirs operate, who could be repurposed to look at this as an alternative technology. And that is all from me. Thank you very much.